tell Zion, and after that we'll tell Zion if he passes or not. Okay. Any other questions, especially Christina?
Yeah, no questions. Very
Awesome.
clear. Thank you.
Okay, so without further ado, let's welcome Zion to give us this talk. Hopefully it doesn't go over time.
It will not. I will do my best, and that actually flows really great into this. So the topic of this is, of course, decompilation, as Fish has said, and this long and winding road. But of course, I have 45 minutes, so hopefully it's not too long. So to preface this whole thing, right? Binaries rule the world. We have these binaries integrated into our life everywhere. We have them in our routers, our very access to the vital internet that we all prolong to use. We have these drones now that have binaries, firmware that run them. Very soon we're all going to be receiving all of our Amazon orders just through drone. You don't want a drone crashing into your house. You want to understand these drones. And then, of course, we even have smart cars now. These smart cars, you might find yourself only being in smart cars in the next few years. If you've taken an Uber around here or Waymo, you know that smart cars are becoming integrated into our normal society. And all these have a critical thing in common. They're run by binaries that are hard to understand. And in addition to binaries being, so critical when you don't have access to source, even when you do have access to source, such as being a developer in a little known project known as XZ, where you have integrated backdoors, right? These backdoors may not become obvious until you're actually looking at the binary. There's a mismatch between your source code and your binary, and this is a part of how the backdoor was made. And so there's kind of been this critical need for understanding what exactly is in my binary, even when I have the source code. So don't fear, decompilation is here. Like a superhero, if I could make like a decompilation with a cape, maybe Ida with a cape. So the outline of this talk is to kind of go over what is decompilation exactly, some of the fundamentals, these pillars of what make decompilation so hard or so interesting, and then evaluation findings, some recent work that we did, and lastly, some future areas for exploration. So who am I briefly? Fish already did a great job, but in case you didn't know, I'm the guy wearing the Shellfish shirt. I'm one of the Shellfish members, this epic CTF team that is also participating in AICC and other cool things. And I'm also a native Hawaiian from the Big Island. This last part's important because I hate pineapples on pizza. Keep them away from me. So what is decompilation? Decompilation is the process of turning a program back into something understandable. So for this talk, we'll mostly be focusing on binary programs or compiled programs because there exists different types of decompilation. You have Java decompilation, you have Python decompilation. Recent works has even said decompilation when you're turning it back into a neural network. So this is different definitions of decompilation. For this talk, it'll be mostly binaries. So you're trying to get something that kind of looks like source. You're trying to get a higher level understanding. May not be exact source, but this is kind of the goals of decompilation, is to lift something hard to understand into something easier to understand. There's a lot of different reasons you might want to do that. Some reasons is for malware analysis. You need source so you can understand if this is malware. Maybe you want to patch it. You want to have something that's been deprecated and now you want to fix it up. You want to look for bugs, or maybe you just want to know what it does. Maybe you don't want just your random drone flying around and you have no idea when it might crash into your house. So to pivot this a little tighter, when we talk about human-centric decompilation, we really are talking about humans. So you have this kind of inverted galaxy brain meme here, where we're trying to go from, you don't have to have a galaxy brain to understand what the program is doing. You can be all the way here at the bottom with the tiny brain, but decompilation makes it possible to understand programs. So why is it hard? So you take, some handsome fellow, some source code, and then you compile them up, right? And what you get at the end is something that looks something like the original photo. This original photo was, pretty good pixelation. This one on the right-hand or left-hand side is, of course, a 9:9 image. If you only had that, I ask you, who's actually in this photo? I don't know. So the current belief is that this is a very lossy process. When you compile something, you lose a lot of information. And this is kind of the end result, is I have a 9:9 image. Please tell me who's in the image. And that kind of takes us to, how did this all begin? So some of the origins of decompilation, although we all kind of know the hint here, we're going towards the 1994 dissertation by Dr. Cifuentes. Before that, we had some even earlier origins dating all the way back to the early 60s. You have a Neliac decompiler. I don't even really know what Neliac is. It's a programming language that I know that Lockheed Martin was concerned with, that they liked a lot. So they had different people over time kind of develop this way to understand what exactly their compiled program was doing. Their main purpose was for when they lost source code. I don't know how they lost source code, but sometimes they did. They wanted to fix up their programs. So their main purpose was for recompilation. Now, of course, the academic origins of when everything starts to explode into these fundamental areas is in 1994 with Dr. Cristina Cifuentes' dissertation. And this sets off the foundations. And it's very awesome, very epic that we have her today, as one of the committee members. So this DCC decompiler that was part of the dissertation sets off the very first kind of well-known pipeline for decompilation. You take some machine code, you do some kind of lifting to get a control flow graph. That control flow graph gets turned into some linear code through structuring, and then maybe you fix up the code after that, and it turns into this nice kind of optimized format. And these optimizations and these data flow analyses were based on, as Jay said last week, a very well-known book, the Dragon book, as many of us refer to it, about compilers. And this really starts our decompilation research areas of where it all begins and how we divide them up. So to preface this, right, a lot of these things I had to kind of cut into their own areas because there's not so much literature on boxing what parts of a decompiler is well known. So we have, these two kind of sets. We have the fundamental research, and then we kind of have these what I call applied research. So you have something like symbol recovery, recompilability, there's going to be vulnerability analysis, and then you have the fundamentals. So this is all applied research. To preface all of this stuff, if at any point you find any of this really cool fundamental research interesting, as a result of this comprehensive exam, I went through about 100 papers. About 80 of those papers found their way into this decompilation wiki. So around 80 citations have been compiled into this nice work. Almost every kind of explanation I do, any citation I use, and even images and examples are also found currently in the decompilation wiki. Yes?
Did you tube this, or did you get 48 just organic start?
That's just organic. Nobody knows about it. I plan on making it public on Wednesday.
Mastodon.
Yeah, or on, yeah, sure. Yeah, so that 48 is just natural. I don't know how they found out about it. Somebody leaked it. So yeah, it's up right now. If you guys are interested, everything in this talk is already there. So I spent a copious amount of time, splitting these up and putting them in this nice format. So let's get to these awesome fundamental research areas and why exactly are they fundamental? So one way to understand why these are fundamental is because how they affect each other. For instance, control flow structuring is not possible without CFG recovery, and neither is typing. But in addition to that, the way that you do control flow structuring can affect how you do typing and can also affect your CFG recovery. And as an optional last phase, you have this evaluation, which affects all of us in how, what exactly are we optimizing towards? Because there are different goals for different types of decompilation. You can do decompilation for recompiling, vulnerability analysis, understanding. And these create the fundamental areas because they affect each other and decompilation can't exist without them. So let's start with control flow graph recovery. Control flow graph recovery tries to take machine code and turn it into a graph, as it might imply here. There are different phases for CFG recovery. There is disassembling, there is lifting to an intermediate language, you have identification of function boundaries, and you even have resolving indirect control flow. All of these areas present some interesting problems. In disassembling, you might want to have different types of disassembly. There was good papers on using data log that allows you to have more, reassemblability. The intermediate language you choose may, differ what exactly your decompilation can do. The function boundaries are, of course, important for decompilation because those are kind of our atoms for analysis. And indirect control flow has got increasingly harder as we get harder languages. To kind of riff on what those harder problems are, right? These problems in CFG recovery, which continue to right now, first, how do you measure correctness? It feels intuitive that you would just measure correctness by looking at object dump or something, but object dump is only one way of creating disassembly. Some recent work has looked at instrumenting the compiler to understand more closely if you have the right graph, but this isn't perfect either. And how do you resolve these indirect jumps that come from higher level constructs like C++ stuff, or even things like Rust? And lastly, how do you disassemble an architecture you've never seen before? That's of course very open work. Now, to ground all of these fundamental areas, I provide an example of what exactly is wrong right now. So for every one of these fundamental areas, I have one tiny example from IDA-Pro to show you that things are still broken currently. This is one thing we found in format core utils. If you don't know the format binary, it is a binary that exists on almost every single Unix system in the world. It is a very fundamental program. It just allows you to format text. In this example, you have source code on the top and you have IDA-Pro on the bottom. Now there's problems here. Aside from the names being different because of inlining and macros and stuff like that, you have a fundamental difference in the control flow that ends. Now, the reason for this difference is actually quite interesting. What IDA-Pro doesn't know here is that error is a optionally exiting function. It means it doesn't always exit. If you pass error the argument 0, it does not exit. It just returns. But if you pass error the argument 1, it exits. And the way you can tell this is wrong is because in IDA's graph, there's an edge here after error, and that actually shouldn't exist. This is one problem of CFG recovery. The specific problem is that IDA doesn't know as much as the compiler does necessarily here, or even that error, is something that can optionally exit. So on to type inferencing and variable recovery. Type inferencing and variable recovery, another fundamental area is, yeah.
So can you go back?
Yep.
2 slides. What kind of high-level problems does it show, or is the only problem with understanding the error function? Are there other functions that will introduce problems like this?
That would introduce like these like successor problems.
Yeah.
Yeah.
Or like, so my understanding is that this is you're referring to a problem that the decompiler / disassembler sees the binary differently from what the compiler was seeing.
Yep.
Where are other cases? What are other cases that such that would be a problem?
Yeah. Another great case of bad control flow graph recovery is any kind of structure that gets turned into an indirect jump. Lots of structures exist, as you guys might know, like switch statements. Switch statements are almost always made as an indirect jump. That's just one example. If you have other indirect jumps like this, for instance, they do this in C++ a lot for virtualization. The control flow graph is what is the fundamental problem. There is a mismatch in what the compiler knew and what the CFG recoverer knew. Yeah. But this is one nice motivating example. It's easy to understand. So onto type inferencing and variable recovery. This is concerned with turning data and where it is stored into something understandable and condensed. For instance, this conversion to an int. There's been quite a bit of approaches in this area. Variable use analysis. We have library awareness, also known as type sinks. We have this emulation, which was a very cool paper. And then we have push-down typing, and lastly, machine learning. These different approaches have all had, varied metrics for seeing how good they're doing. For instance, conservativeness. But for the general case, all of them use source as their ground truth, and they compare how often they get the right type. I think some of the most interesting work that comes out of here and some of the hardest problems is in this variable use analysis. With any kind of alias and understanding uses of types, you have to do a large scale static analysis, and being able to scale that out further and further to dozens of function uses, so like inter-function analysis, this is where a lot of the problems come from. This is a fundamental issue that still needs to be solved. So the motivating example, all of the motivating examples, by the way, are just from that one function and format, just to kind of emphasize the point that there's problems. IDA-Pro on the right, source on the left, you have this format function, which always returns a Boolean. And the Boolean here should be stored in v13, which is the variable name OK. Now the problem here is that OK didn't get recovered correctly with its type. It believes that OK is an integer, but OK is less than an integer. Right, so this is a problem because this low byte reference into v13 affects the rest of the control flow of what exactly can be reduced with v13. And so, this is one example of where type inferencing gets critical, and it will also affect later control flow structuring. Now, onto my favorite area, which is control flow.
Sorry, Zion, can you go back?
Yeah. Yep.
So you said this was critical. Why?
Why is it critical? I wish I had more code to show up here. The reason it's critical is because this V13 being accessed as a low byte, now it believes there is more space that is needed for this variable. It clobbers some other variables, and that clobbering causes more statements, which then also causes if statements to be non-reducible. When I say non-reducible, you can think like, if I have two if statements layered on top of each other, if it were just two if statements, I can condense that into just an or, like or one or two. But if there are statements in between it, we get this problem. And the statements get created when you have this V13, which causes more statements from having, more accesses. So that's kind of the staggering effects of this mismatch in typing.
I see, but why is that critical? I mean, critical to me means like something kind of like a critical severity vulnerability is very bad.
I see. Okay, I guess I wouldn't say it's critical, but for the sake of human comprehensible decompilation, it's definitely high on the tier list. Because this overuse of a variable is not good.
And so what do reverse engineers do about this?
Right now, reverse engineers would probably retype this if they can. Sometimes you can't because of the overlap of variables. So they'd probably try to retype this kind of human in the loop typing and restructuring.
Retype V13.
Thanks.
Yeah, retype V13.
Hard to do with that call.
Hard to. Any other questions on typing recovery, on type stuff? No type. All right, control flow structuring, a very fun area, my favorite area, and something we recently worked in. Control flow structuring is concerned with taking now these CFGs that hopefully have type information and have been lifted and turning them into our nice linear code that we're familiar with. So the origins of control flow structuring, kind of dating back to Dr. Cifuentes' work, has been about pattern matching. You take a pattern that you're well aware a compiler does, and boom, you turn it into this linear code. So we have this example of different schemas taken directly from the dissertation here of things that we believe the compiler will output. For instance, a classic diamond, you have a switch statement, you have some loops, some very cool schemas that represent what exactly you're matching. Yes?
Which dissertation?
Which dissertation? Dr. Cifuentes' dissertation. So structuring can be impactful for readability. This readability is kind of critical to human-centric decompilation. So here's one example of how you might convert this graph shown in the middle into some linear C code. You have this nice linearization, and you're kind of forced into one go-to here. Similarly, there's actually another way to structure this code. You can structure it like this on the right-hand side. Now, there's definitely better and worse ways to structure code because of how many scopes are now shown in this code. For instance, this left-hand side has less scopes than the right-hand side, but they have the same amount of go-tos, and these are also semantically the same. So this kind of, pushes us towards the answer that structuring does matter. Like we need to find better ways to structure code, or there exists some right answer for human readability. Right, so you have this guy, he has more scopes. So the problem here was that we had this nice schema down here, the diamond, the classic diamond. And we also had this guy who created this kind of cut right into the middle of the diamond. And that's where this kind of illegal edge happens. So you had a chance to turn one of these edges into go-to.
What is a diamond?
What is a diamond? Here, this is a diamond. Yeah. This is the nice diamond structure of nodes where you have one parent, children, and then they come back to a common successor. Yes.
What code structure does the diamond represent?
I see. A diamond represents a classic if-else structure. You can convert one diamond to an if-else.
Is it your term?
The diamond?
Mhm.
No, this is a software engineering term.
Where is this term coming from?
I see. This term is coming from, do I have a citation? I remember it being referenced here in the Phoenix paper, but this is coming from a 1970s not control flow recovery, but a CFG paper in software engineering. So I can add that to the post citations afterwards. So yeah, you have this edge and you have these choices. So there's something kind of interesting here. This is more of a kind of a theory of maths that you can compute on any given graph. So on a graph where you're trying to do some structuring, you have this minimum combinations of how many different ways you could turn the graph into linear code. Here are some kind of guesstimates of how you can determine how many combinations. You have the number of branches times this unstructured regions, which is just the go-to edges, and then the overlapping struct choices. So in this case, you have this number. This comes from over here, these two, and then the unstructured region, the one go-to that you know has to exist, right? There's no way around that go-to without duplication. And that creates at least 24 choices. So this is some very quick and dirty math that you can maybe use to guesstimate. I think it's a very cool area. Could use some more understanding it. So there are
Sorry,
different.
what's the point of this guesstimate math?
The guesstimate math is to illustrate how many different ways you can turn a single graph into linear C code. And that means there are this many choices you need to choose from when you're writing a decompiler.
Is that combinatorics? I mean, isn't that counting different structures?
Counting different structures like.
Combinatorics, the field of mathematics called combinatorics.
Yeah. Yes, I'm a little confused in the question.
Why is it called Zion's math on top of this slide?
Oh, the reason I call it Zion's maths is because it's not, there's no defined literature yet for computing how many different structuring choices you have when given a graph. Yeah, so it's a guess based
This
on.
is the upper bound estimate.
This is
Upper bound guessing.
This is lower bound guessing.
Lower bound.
Yeah, lower bound guessing.
Yeah, so I still don't understand why it's a guess. It either is or it isn't, right? I mean, it's either a good estimation of the upper bound or it's not.
The reason it's a guess is because the number, when you structure one go-to, there may be more go-tos that result of a bad go-to. So I guess that's where this guess kind of comes from here. For instance, choosing which edge right here, this golden edge, choosing that golden edge results in no more following choices, but if you had chosen, for instance, the B to D edge, it creates more choices. And I don't know yet how to represent that mathematically. That one choice can result in more choices. That's why I kind of say this is the minimum combinations.
So, but if it's not accurate, then what's the point of this?
The point is just to get an estimate in your head of, at a minimum, how many different ways there are to turn such a tiny graph into C code. Oh, yeah.
Why do you need that?
Why do you need that? The point here is kind of to motivate you towards that there is a lot of choices you need to choose from in any given scenario. And that if you have all these choices, which one is the correct choice for humans in this case?
So you're saying out of those, there's a single correct choice.
Out of these, there's possibly a correct choice that is the most readable. I think this one on the left-hand side is the most readable choice you can do, but there's so many combinations that I didn't go through all of them. Yeah. But yeah, these maths are very guesstimating.
Like, how do you compare them? So if one is 24 and the other one is 20, does that mean that graph is more easily structurable?
I would say if you had less choices, it is easier to choose something, probably. It's kind of hard to say. My guess is that, yeah, if you have less choices, that is an easier way to choose.
But if you're not representing that gold case where one choice leads to 10 more choices or 0 choices, whereas another choice leads to way more choices, then can you compare those numbers?
This is true. These might be non-comparable.
One way that I can think of why this is useful is that if this is a low enough number, right, we can actually enumerate all possible combinations and then select the one that we want, select the quote unquote best one out of a structuring algorithm, right? Whereas, if you have way too many combinations, then searching the entire space and selecting the best one may not be easily done. But I think this is a very good discussion that we can have, but maybe after the entire talk. Let's go a little more.
Sure. So let's get to the actual control flow structuring types. In our Sailor paper, we define two separate types of control flow structuring. You have schema-based, which has these nice papers, and you have go-to lists. RevNG is listed here twice between schema-based and go-to lists, and I'll get into that a little bit, but the main reason is when you have a schema-based structuring algorithm, you usually try to take a pattern and match it to the graph. But in RevNG, they do the opposite. They take a graph and try to match it to the pattern. So they actually edit your graph to make it more like a schema that they know. In this case, the schema is like loops and just if statements. So control flow structuring works. There's been a few works in this area that have really pushed along this line of how can we get better code for a human, or how can we get better code in general, right? We have pattern matching based on semantic preserving. We have go-tos, which get eliminated using Dream. This is all based on condition bounding. We have this block duplication, which is from RevNG, which, like I said a second ago, takes a graph and matches it to a schema instead of a schema to a graph. They do the kind of opposite here. And then you have this reversion that we did in our Sailor paper, which is about reverting go-to causes, which we believe to be compiler optimizations. So to kind of show off these problems again in this control flow structuring, we have IDA-Pro and we have the source, and we have these main differences in how many calls is being called to xdec2max here. Xdec2max is only called twice inside of the source code, but in IDA-Pro, we have 3 times. And in addition to it being 3 times, we also have these go-tos everywhere, which are a result of the duplication of the code found in the source. So kind of the surprise to this, if you read our paper, the reason behind this specific structuring failure is due to compiler optimizations. So if you revert those compiler optimizations, which originally caused 3 calls, which really does not exist in the source code, then you can get back to 2. But, you know, not everything is perfect. The world isn't perfect after this. We still have these problems. These problems of, I said, kind of these combinations again, these different ways to choose. The branch was flipped. We chose the wrong flip here. And this is just an arbitrary choice, right? You can choose to do not V5, you can choose to do V5, and it changes how exact you are to this source. In this case, because there's the same amount of scopes, no matter what you do, it seems like it's okay. But you know, you can imagine if we layer this on more and more choices, these scopes get bigger and bigger and bigger. So although we solved one problem about these duplication, there are still more problems. And on that, take a short break, real quick. Any questions? Yes.
The previous slides, you displayed several different qualities about source code, number of scopes, go to separate variables.
Yep.
Are you aware of a paper that has tried to find a minima of all of these different qualities to determine what optimal readability is? I mean, obviously, it's very subjective. What
Yeah.
you consider readable
Of
may not
course.
be what I do, and indeed, many programmers format their code differently.
So I'm gonna wait.
Aware of a study that's tried to find what.
I'm gonna wait on that one because the very next section is evaluation, which we'll get to this, but short answer, there has been very recently at ICSI 2024. So there has been.
So then with the previous slide, like the example that you shown, it
This one?
was, yes, this one. So there's more calls, but it's because of compiler optimization.
Yep.
And what you're saying is that because you're aiming for human centric type of decompilation, you really do not want to be faithful to what's in the binary itself. You want to be able to lift it even further.
Yeah, so it's kind of this philosophical discussion of what is your target audience, I guess, with your decompiler. In the
Right.
case of Sailor, when we tried to target source code exactly, we assumed that the source code in like good binaries is fundamentally the best representation of what the human was writing. So we're kind of, you know, putting our hopes here that the programmer really knew what they were doing and they wrote code that represented that. So in this case, we think, yeah, although there are 3 calls inside of the assembly, as a reverser, you may want to only look at 2 because that's exactly what happened in the source code.
Right. Okay.
Yeah.
Thank you.
What about, are there any other use cases for that, Zion, or is it only patching based?
There's, you know, some patching. There are some special cases about vulnerability analysis where you can imagine that if the compiler is duplicating code everywhere and you don't realize it is, you might patch it once in the source code and it might get split out and duplicated. And you actually have two places, one where the vulnerability could exist and one where it doesn't in your new patch. So patching is still kind of this motivating example, but it has effects of vulnerability, and it can also have effects of, like malware analysis, where if this duplication happens too many times, the program looks like a fundamentally different program.
Cool, thank you.
All right, let's get through this last fundamentals, which is about evaluation. And this is how you measure if decompilation is good, if it's bad, right? This is a still very active research area, and how we know when we've done something well, right? So there's been kind of three differing ways, different paths to evaluate how good decompilation is. You can use a human to evaluate it, you can use software engineering metrics, or you can use source relative metrics. Each one treats this as a different problem. The human one treats it more subjectively, like decompilation is subjective to its human user, right? Like there's maybe some kind of commonality of how humans perceive it. Software engineering, of course, treats this like a standalone thing, as if decompilation itself is software and you're using or reading software. And source relative is more of a machine translation problem. So we'll go to human here. There's been a few interesting ways people have kind of diversified out in evaluating how humans think decompilation looks. There has been malware reversing studies where they give the humans malware, they tell them use the decompiler, and then please tell me if you feel this was better or worse. This was in the Dream++ study. You have large team reversing. This was done by a nice paper here about the industrial age of hacking. This one is less about decompilers specifically, but how humans use tools is also related to how they would rate decompilation. CrackMe's, which is from disassembler usage, and then handmade or human-made decompilation. This was in a decomperson study where you had a bunch of humans try to make their own decompilation, and then they're optimizing for byte equivalence. These have been all kind of side channels to evaluate how humans think this code is good. What's not shown here is that there is one extra paper from ICSI. I haven't actually been able to read it yet. I've only been able to read their code, and this is because it's not out yet. This paper is on trying to take these metrics and learn which metrics are associated with best human responses. I, of course, haven't read it yet, though, so I can't fully say. I've only reversed some of their code that's public.
Another paper that's missing?
Yep.
Smart words.
This, true.
Yeah. So which I really wanted to say there are many papers that are missing, but you don't have to list all of them, right? So you don't have to say which paper you did this happening.
Fair enough. So we have software engineering metrics. These software engineering metrics are really based on what code, when it is just code, looks the best for humans. There have been reducing go-tos to 0 because go-tos are considered harmful, cyclomatic complexity towards 0, and of course lines of code towards 0. And these have all been different decompiler works, all which happen to be in structuring, which say, hey, decompilation itself should be treated as standalone software, and we should just try to make it look better in general. And so these different metrics that they've used have been kind of irrelevant to what the source code actually looks like. For instance, McCabe's cyclomatic code complexity here says that something is more complex than it's bad. So they will always want to go towards 0 in this case. And then you have source relative evaluations. Source relative evaluations are about taking your decompilation and comparing it to the values found in the source. So most of these first few are from our paper Sailor, which says, hey, your metrics are only good when you relate it to the source code. This is, of course, our motivation that source is still the best way to represent decompilation. You might look at go-tos, right? I have all my go-tos, but it only matters when I see how many go-tos was in the source code. For instance, some people might argue the Linux kernel go-tos are a good use of go-tos. And I'd say a lot of them are. Graph edit distance, which is again, how close to CFGs are when given the source, Boolean expressions, function calls, and then variable names were used in a variety of different, naming papers. In that type recovery I showed, there's been work by, augmenting decompiler output. This is Dirty. Dirty looks at, can we estimate function names and types? They use the same idea that source relativeness is a good way to measure your decompilation. So they measure it based on how close their variable names are to the source. And lastly is fidelity. This is a very recent paper in Usenix 2024, which is about small problems in decompilation and how they relate to source code. This one, of course, is not automated. It is generated by humans, kind of taking two parts side by side like we did throughout this presentation and looking, hey, what are the real problems? So this one is more of a kind of a comprehensive study of different problems in decompilation. To give you a last motivation of just this source relativeness, here is a snippet from IDAPRO and Anger's implementation of Dream. The reason this might matter is for these booleans on the bottom, right? If you don't know what the source code looks like, you might say that it doesn't, hey, that's probably good, I think. But in reality, in the source code, this is still the format function. There's only one condition here in the source code. And this is a bit of an illustration of how source relativeness is important. I saw a question a second ago. Anybody? Nope, okay, cool. So just to kind of elaborate on this from our work in Sailor, we did a larger scale source relativeness evaluation to see how close decompilers were to the source. I've tried to take a bunch of numbers and condense them into one tiny graph here. So this yellow bar is go-tos times 100. So you multiply that number by 100 and that's how many is present. This is across about 10,000 functions in 26 different packages. You also have the CFJED, which is our graph edit distance, but for control flow graphs. So you'll notice our recent work Sailor is coming striking, in striking distance with IDAPRO on this source exact, graphs. Of course, they're still winning. They are winning by 0.12 here. We're very close though, and something that's interesting is that our go-tos are very close to the source. Maybe I shouldn't say very close. I should say closer relative to IDA. This kind of pushes us towards the question that maybe the best decompilation will get us to a lower CFJED score, but a go-to count that is closer to the source. And we need to balance between the two. As an example, as a counter example to this, you can see Dream on the far right, which of course gets rid of all go-tos. They're a little further from source, but now their graph edit distance is much higher. So you need to balance the two. In a perfect world, you would just get the exact go-tos and you would have a 0 graph edit distance. But until then, you need to balance between the two and minimize both, equally. Another thing you might notice from this relative evaluation of how close these decompilers are is that even in the best case with IDAPRO, we're still very far. IDAPRO has an average graph edit distance of 22 edits. Why? This is something that we're still trying to answer, is why is there so much edits left across all these binaries? Many of them could be due to our graph edit distance being an approximation, but we think there might be other, layering problems that we're not addressing. For instance, as you saw, the choices that you can make during structuring have lingering effects. Nice little slide on decompilers that might be a little hard to read. Here is a list of them. You can find them on the Decompilation Wiki in the Decompilers tab. We have a few listed here. All of these are binary decompilers. That's what the 0 means. And the skull means they're no longer supported.
So
yep,
there are obviously more binary decompilers in
yes.
the wild. What is the criteria for you to select some of them and present them in this table?
In this table, these were just the ones that I could find fast.
Like they work fast? Or?
The most publicly visible decompilers I could see. So there's some
by GitHub stars,
just kind of word of mouth.
So it's Zion's math again.
A little bit of Zion's back. Zion's decompilers, but it was hard to find more outside of this list. I think there should be more. There is more. These are just the ones that I could fit in a table that fit on the slides. I could make them, there is more. So I think there is more to list.
One that's missing, there's a fork of Anger that implements the Sailor structuring algorithm. That might be a good thing to put up here as a different project.
Yeah.
Or over time.
Are you accepting PRs?
Yes, sorry, PRs are fully accepted. And
but in all seriousness,
yeah.
Are you listing academic decompilers, which means decompilers that may not be open sourced or made available, or are you listing decompilers that are available for use, but are not necessarily described in any academic work?
I see. All of these decompilers that I've been listing were available. So all of these are available, even if they're not open sourced, which are of course downloadable. So I'll wrap this up now because I know I am at the hard limit We're very close.
Just have 10 minutes.
Oh, yeah, 10 minutes, never mind. So we have this applied research just to kind of throw this in of different ways people have been extending this research in decompilers. You have symbol recovery, which you've heard a little bit about. We have, of course, Varbert there in the listing, Varbert in our symbol recovery listing. We have code similarity. Code similarity has been kind of a newer topic that they've been using decompilation for to see how close this might be to another snippet of decompilation or source code useful in malware analysis, but also useful in detecting inline code inside of decompilation. You also have vulnerability discovery, a little known paper called The Convergence of Source Code and Binary Vulnerability Discovery, a case study, little known. And this paper looks at how close has decompilation or our tools gotten to being able to apply source code tools on them. And it's interesting because all of these different applied researches of decompilation give new kind of ideas on how you measure the quality of your decompilation. Since symbol recovery, code similarity, and vulnerability discovery can all be rapidly different use cases that require different types of decompilation. So I'll talk about some future areas that I think could be interesting. Based on all of these kind of works I've compiled and things you can find in the Decompilation Wiki, these are some new stuff that I think could be explored more. Evaluating decompiler quality, right? What metrics align with human evaluation? I haven't gotten to read the ICSI paper yet, but I'm sure they'll get closer on this one. What exactly of all those metrics I listed, which ones align most with how humans use decompilers? Is there some kind of correlation we can do between them? Is source exact decompilation the best? You've already heard this in the talk, but is this really the best way to represent decompilation? Is it context sensitive? Right, does it depend on your context of use? Reversing, exploiting, patching, right? Are these different formats for structuring decompilation or for even typing, for even control flow graph recovery? And then lastly, right, in this list of quality, is collaboration something that you need to concern yourself when evaluating decompiler quality? Can I collaborate with someone more easily? So collaborative decompilers, there's also exploration for these kind of areas that build on each other, right? You have decompilers interacting with humans, you have decompilers interacting with decompilers, with debuggers, with AI, right? What are the best ways to interact tools with decompilers, and does that affect the reverse engineering process? Like, is use in a debugger fundamentally better when you have a decompiler in the debugger? Or is AI made better with decompilation when trying to understand a binary? Right? These are all collaboration tasks for a decompiler. Human is one of those collaborations. And this kind of last topic area of human in the loop structuring. You've seen all of these crazy choices we have for structuring. In a graph of only 5 nodes, there were over 24 possible choices. Can we measure how easy it is for a human to choose the right structuring choice? Is there decompilation that is more malleable, that is more useful for humans in structuring choices? Can structuring abstractness be scaled? Do you need to have, source exact only or super verbose assembly? And can I choose a slider between them? And on that last note, I think, there's a lot of different ways you can choose to structure decompilation. There's a lot of ways you can choose to measure it and increase these fundamental areas. And I think, this new areas in decompilation have a lot of future growth, a lot of upward mobility in the research scale. And on that, I'll ask if you guys have any questions, anything regarding evaluation, structuring, or any of the fundamental topics we covered in this comprehensive exam talk. Yeah.
Are you,
Don't ask about Sailor integration.
alright, other questions?
Also don't ask about coffee and snacks.
Alright, no more questions.
Awesome. So thank you very much for giving the talk. Do we have any questions? When you start counting, 15 minutes now. Also including people on Zoom, but please go ahead.
Very good talk. I really enjoyed it, and I like that there's a human somewhere, and I'm hoping to see more papers from you.
Thank you.
I want
Hey, excuse me. People.
Yeah, so they can hear you on Zoom.
Thank you.
I'll just repeat myself. I was saying that it was a very nice presentation, and I'm excited to see that there is a human in the loop that's going to be interrogated and investigated in the future. Can you talk to me a little bit about the motivation to consider human
The motivation.
in these kind of studies and to better understand decompilation metrics?
Yeah.
And where is it literally really coming from, in the sense that, is it largely the readability or anything else as well?
I see. I think the reason there's so much motivation, at least in the way this comprehensive exam was laid out, which is of course human-centric decompilation, is because one is my own motivation, right? I use decompilers all the time to understand programs, and I think it's something that helps me understand them. Kind of going out further from that, I think there's still so many problems inside of binary analysis that it takes a human to understand what a program is doing still. Maybe GPT is changing that a little bit about what is comprehensible with source and stuff like that. So I think getting a human in the loop of understanding how good decompilation is kind of critical, because decompilation really is motivated for, I think, in the beginning, humans, right? How does a human understand this program? Source code is useful for humans. So getting humans into some kind of evaluation form here, I think really helps extend the field, not only useful for experts, but also just for the generic use of, you know, programmers who may want to use decompilation in the future to understand what their programs do.
Most people would agree that correctness is paramount when you're doing decompilation, right?
Yep.
In addition to readability.
Yep.
Do you think that recompilability and using byte exact recompilation is the holy grail of metrics in measuring correctness, or do you think that there's other things that we can use to determine whether our decompilation is indeed correct?
Right. So there's, I think, two differences between correctness and then like what is the best decompilation. This byte exactness, in our Saylor paper, we actually have a little section on byte exact decompilation and how readability might relate to that. We found in the Decomperson study where they tried to create their own decompilation that was towards byte exactness. Over time, their readability kept getting better and better and better, and then at a point it flatlined, and then it got worse. And that last bit where it flatlined and got worse was where they finally made it to byte exactness. So there seems to be some difference between readability and byte exactness. So I think on that note, right, recompilability is extremely critical for useful decompilation. But at the same time, it is not necessarily the holy grail of readability.
So I have a follow-up question from the first question that was made. Mine was more like about who is your target audience, because I think like what type of code a developer may want to see may be slightly different to what a security researcher may want to see.
Yeah, yeah. So the target audience, you know, at least for this initial work, has always been reverse engineers, right? A security-minded person. I think you bring up a good point about this, because decompilation, again, can be tuned towards, you know, understandability versus exploitability, where in the case of a security researcher, you might be more concerned with, is this a safe program? But I think this target audience can be expanded, and as my own goals, you know, for the next maybe 10 years of my life, or what these goals are for decompilation, is that they can be used by just a normal programmer, by someone that programs in C or, you know, Rust or something like that, and it gets them some code that is somewhat understandable. And so I think you make a great point about it being different based on who your target audience is. In the case of like a programmer target audience, I do think going towards more source-like thing is something that's probably better.
Right.
Yeah.
Yeah. Okay. Thank you.
Awesome.
Okay, so you mentioned 3 types of decompiler in your talk. Decompiler for like understanding, decompiler for patching, decompiler for vulnerability discovery. So what are the differences between them in terms of their goals and focuses?
Yeah. The differences between them really, I think, scale between verbosity and stability. Where in the case of exploiting, like Dr. Cristina Cifuentes brought up a few minutes ago about, do you really want only 2 calls instead of 3? I think as an exploiter, you don't want that. You don't want this changing of what the assembly looks like, right? You want exactly as assembly intended, just, you know, simple compiler optimizations on top, like dead variable. On the other hand, for patching, right, you may just want something that is the most stable. You might be okay with duplication, you might not be. You just want to make sure that whatever you compile is most likely to get byte equivalents. And then in, just general understanding, like in the case of like a normal programmer, I think they just want source code. I think they just say, give me source. I don't care about all this assembly craziness. I just want to read my precious Rust code. So I think they want something like that.
Any other questions?
I have another question related to type inference.
Yeah.
Like from the talk, it wasn't clear like what work you've done in that area. Can you expand on it?
What work I've personally done in type inferencing?
Yes.
I see. I have done almost no work in type inferencing. The closest I have is on the Barber project, which is more about variable naming. And so that's kind of, how machine learning could relate to learning these opinionated things in compilation, like types or names. So I haven't actually done much work in typing. That part was mostly about the literature review, as was the control flow graph recovery, right? I haven't done much work in control flow graph recovery, although all of those things, CFG recovery, typing, structuring, they all became problems in Sailor that we had to mitigate in some way. So mostly just technical knowledge, not so much in the academic world for typing.
Okay, thank you.
So I have a question. This is looking more a little bit towards the future.
Yeah.
But you just mentioned that in your paper, Sailor, you had to deal with all these other problems.
Yeah.
You dealt mainly with control flow structuring in Sailor. But what do you think the next big topic essentially that you think you could tackle that would help towards better decompilation? Would better type inferencing allow for better control flow structuring?
Personally, I think that the next area I would like to explore, aside from collaborative decompilers with our work on BinSync, I'd like to look into what structuring algorithms are really related to what types of use. So for instance, my hunch, my gut feeling is that maybe malware analysis really is better with Dream. But for something like looking at core utils, you really want to use Phoenix. I'd like to know which of these structuring algorithms and how much they structure is related to your use case.
I see. And then do you think the application of those structuring algorithms can be, do you think the application of the structuring algorithms can be done deterministically, or is this something that you're going to have to hand over to an AI model, or something that's going to be a checkbox on the side of Anger's decompiler?
I think there's some simple metrics that you can apply immediately. For instance, like how many conditions are in a line. If you see more than 6, don't do Dream, right? Like you can cut that really fast. So I think there are some deterministic things you can choose, but a larger part may come from either a human in the loop or some kind of AI system determining what's the best.
Thank you.
It's a great question.
So you talked about different applications of the decompiled output, such as patching, exploiting, or just understanding this thing. So are the kind of structuring or decompilation process required to get to kind of target that kind of audience? Are they something that you can sort of stack, like how compiler has optimization passes? Can you have separate de-optimization passes or so to create like this scaling of abstractness?
Yes, yeah. In the way Anger decompiler is set up right now, we kind of have that already, where you have de-optimizations that get layered on top of each other. You can disable them. We of course don't have any understanding of a scale, right? Like which ones do you actually want to disable if you want it to be less verbose? We don't know all of them yet. There are some simple ones like removing a stack canary being shown in decompilation. You can just get rid of that if you just want understanding and you don't care about function calls. So I think we have something close to that. We just don't have any automated way to know what to disable. Right now, it's just a big checkbox where you choose. Yeah.
Christina, you have a question?
Yes, yeah, I have a question related to during your evaluations, like have you considered looking into like one-way functions? So like if I have a conditional and that conditional ends up being based on a one-way function, then the code, it may not actually jump anywhere, right?
Can you elaborate a little on this one-way function? Do you mean like a hashing function or something of that sort?
A one-way function is a function that you cannot reverse it, right?
Yeah.
And so I cannot tell ahead of time if this is going to be like a true or false. So I could potentially have a one-way function that means that it's always going to be true. And therefore, any false branch really doesn't exist in the original source code, but it would exist in the decompilation if you assume that the conditional will have an if, a true and a false branch, right?
Yes, I see. Oh, that's pretty difficult. Yeah, I'm not sure yet on that one. I'll have to look into that more. That's pretty interesting.
Yeah, it would be cool to look into that. Yeah.
No, yeah, we didn't consider these cases inside of Sailor, and it can be, you know, like a potential flaw in this graph edit distance, where you have cases like this maybe being at compile time inserted into the code. So yeah, I think cases like this exist.
Right.
Those
Okay,
cause
thank you.
issues, right?
I see.
And you're literally helping with the paper that's doing it.
Yeah. the Usha, yes, yeah, cool.
So it seems like as a result of compilers having lots of heuristics and doing these not arbitrary transformations, but slowly knowledge has been built up, let's do these transformations.
Yep.
It seems like decompilation therefore requires lots of heuristics and lots of figuring out how to unwind all of this.
Yes.
So I'm gonna ask the beam question, of course, as someone on the outside. What role do you think large language models will have in basically, is there a world in which I give you 100,000 bytes and out comes source code end to end, or is that just not? I guess what's your intuition on this, or what's in the field
My
right now?
intuition is on that single case, it won't work because of how often compilers change. You get these optimizations that are, like you said, being built over time, knowledge, right? So maybe if you had a large language model that was constantly on the jump, right, of these new compilers and got new data, maybe that would be a hard future. I think a better future where these LLMs get integrated is not the full replacement of the components that you saw at the beginning, these fundamental topics, CFGs, control flow graph recovery, or structuring and these type of things. You don't need to replace the whole component. You can replace a part of it. For instance, maybe the choice that you make in structuring time. Which do I choose? I have 30 choices. Can you tell me which one to choose? I think this is a promising research area. Not the end-to-end. Maybe a secondary way that LLMs can be more generic for decompilation is extracting these rules out of the compiler. In a future research, I could see this being a thing where it somehow runs the compiler and it sees the source code and understands what things happened. And we record those. We do the reverse if it's possible.
Awesome, thank you.
All right, we'll take one last public question before this room is dismissed. Any questions?
When I'm looking at decompilation, it's pretty clear what are unknowns, like variable names, v0, v1. Do you think that there's a clear way that we can illustrate in decompilation output or some other type of interface what facts are known and what is unknown and just picked by heuristics or some other metric?
Yeah, I think there's been some kind of attempts with comments where you can say, hey, this type was guessed and there's these possible choices like we have in anger management. I think there's a future for better ways to represent this. For instance, when you're structuring a loop, you could have chosen to structure a for loop, a while loop, an if with a for loop, right? These are things that are unknown, we guessed. I think that can be made more obvious to the user, and this human in the loop structuring becomes more of a reality. How to do that yet? I don't know, but I think it's something that definitely requires research to get better structuring output that's usable for humans.
Awesome, thank you very much, and I would like to thank Zion for your awesome answers to all of these questions.
Thank you guys, thanks for coming.
Thank everyone for coming.
Even though there's no donuts.
You saved them for the private session, right?
Yeah, the private session has donuts.
Maybe that will provide donuts for tomorrow.
Yeah.
We'll see. But well, if you're submitting a CSAT paper, good luck. Otherwise, we'll see all of you tomorrow morning after 5. Cool. Good job. Can you please stop recording?
Yep.
Remove anyone on Zoom that's not in.
I already did.
And unlock the meeting.
I already did that, Fish.
Oh, thank you.